Hello friends, in this video I'd like to solve the following problem from the Romanian District Mathematical Olympiad for 12th graders, 2011, problem number 3. Let f be a function defined over the compact interval 0, 1, let it be a continuous, weakly increasing function, or if we prefer the other terminology, non-decreasing function. Part A. Show that the sequence 1 over 2 to the power of n times sum from k equals 1 to 2 to the power of n f of k over 2 to the power of n over positive integers n, this sequence is weakly decreasing, or non-increasing, if you will. And part B, the interesting part, prove that this sequence, if one term of this sequence equals the Riemann integral of our function, then our function must be constant. So it's a very nice problem. Here are my hints. First, part A is rather easy. So let Sn be the nth term of our sequence. To prove that our sequence is weakly decreasing, it suffices to show that Sn is greater than or equal Sn plus 1, and notice that this is true, and use this estimate. And for part B, since our function is continuous, f is also Riemann integrable, and this integral is actually given the limit of our sequence Sn actually converges to this integral. And now suppose that our integral equals Sn, some term of our sequence, show that our sequence is stable from this point, so it's constant. Sn equals Sn plus 1 equals Sn plus 2 and so on. And now the funny part, consider the interval k minus 1 over 2 to the power of n, k over 2 to the power of n for any k, and show that our function is constant for all dyadic fractions in this interval. If you don't know, dyadic fractions are fractions whose denominators are powers of 2. And also use this powerful fact that the dyadic fractions form a dense subset of this interval. So give this problem a try. Right, so as I suggested, for the sake of brevity, let's call our sequence Sn. And now I will do the following. For part A, I will compute Sn plus 1. And to be clear, I will avoid using sigma notation. So it's 1 over 2 to the power n plus 1. And here we have f of 1 over 2 to the power n plus 1 plus f of 2 over 2 to the power n plus 1 plus f of 3 over 2 to the power n plus 1. I will write one more. Ellipsis. In the end, we'll have 2 to the power n plus 1 minus 1, 2 to the power n plus 1, plus... I need a new page. I need some space. No need for new page yet. F of 2 to the power n plus 1 over 2 to the power n plus 1. Close. Right. Now, see the following. This, since our function is weakly increasing, this can be estimated from above by the next term. Likewise, this with numerator 3 can be estimated from above by fraction with denominator with numerator 4. And so on. Every fraction with odd numerator can be approximated from above by the next fraction. Which means that our sum is 1 over 2 to the power n plus 1. And what do we have? Well, every fraction with even the numerator appears twice. Appears twice in our sum. Right, and now let's see the following. What's happening? Well, these numbers 2 can be cancelled with one occurrence of 2 in the denominator. And we are left with, and here we can do cancellations. First we have f of 1 over 2 to the power of n, f of 2 over 2 to the power of n, f of 3 over 2 to the power of n, and so on and so on and so on. In the end, it's 2 to the power of n over 2 to the power of n. And what is that? Well, this is exactly Sn, which means that our sequence Sn is weakly decreasing. Is weakly decreasing, which closes the proof of part A. Alright, but let's also see one more thing, remark, which will be useful. Remark, if I denote this by asterisk, in asterisk we have equality if and only if and only if, well, in each of these we have equality. So if and only if f of 2k minus 1 over 2 to the power n plus 1 equals f of 2k 2 to the power n plus 1 for k for all k. Maybe let's be specific, from all k from 1 to 2 to the power of n. Yes. Now, for part B. For part B, let's see the following. First, notice that limit as n goes to infinity of Sn, it's actually the Riemann integral of f of x dx. How do I know it? Or maybe before we say it, let's write that since f is continuous, it is also Riemann integrable. It's Riemann integrable. Every continuous function defined over a compact interval is Riemann integrable. Alright, but I claim that the limit equals the Riemann integral. How do I know it? Well, think about how Riemann integral is constructed. When constructing Riemann integral, we are taking interval 0, 1 and we are partitioning into smaller and smaller pieces. For example, pieces of length 1 over 2 to the power of n. And so on. Alright, and here we have our function, let's say. And now, to compute the Riemann integral, we can take values from the left on the right of our intervals. For example, it's something like that. And now these yellow rectangles, their area approximate the integral. And once we take finer and finer partitions of our interval, we'll get closer and closer to our actual value of Riemann integral. Alright, so this is crucial. Now, suppose that we get our equality faster, not in the limit, but Sn actually equals f of x dx or some positive integer n. What then? Notice that we have the following chain of inequalities. Sn is greater than or equal Sn plus 1, is greater than or equal Sn plus 2, it's the result of part A, and so on and so on. It's less than or equal or rather, it's actually equal. We are supposing that Sn equals this integral. Let's write it. Right. But also, let's take a look that this limit, this converges to the very same Riemann integral. Converges to the very same integral. The only possibility for this to be true is that every term of this sequence actually is equal to the preceding one. Because, for example, if here would be were to be strict inequality, then our sequence would get smaller and smaller, but it would be actually smaller than our integral. And it cannot be, it must be equal. So this means that Sn equals Sn plus 1 equals Sn plus 2, Sn plus 3, and so on and so on. Now comes the interesting part. I will describe what's happening. I will not prove it very formally. It can be done via induction, but I will describe what's happening. Let's take interval. Maybe let's make it bigger. Something like that. Let's take one interval, sorry. K minus 1, 2 to the power of n, k, 2 to the power of n. Alright. Notice that since this equality is true, we have demonstrated, it was our remark written in yellow, that value in middle value in our interval should be equal to the next value. So in our case, the value which our function attains at this point should be equal to the value which it attains at this point, middle point. Yes. And now, since this equality is true, we have the exactly same values here and here, in the middles of these two subintervals. Now, since this is the case, we have even more points at which our function attains the same value. And so on. You should be seeing what's happening. Our function attains the very same value at every point marked in green. So our function, it's easy to verify. It is easy to verify by induction that f attains the same value for every dyadic fraction in the interval from k minus 1 over 2 to the power of n open to k over 2 to the power of n closed. But as we go further and further, this set actually becomes dense in the in this interval. Yes, but this set of fractions is dense in this interval. So since f is continuous, and since it is constant, and since f is constant on a dense subset of this interval, our function must be actually constant on the whole interval. Must be constant on the whole interval, closed on both sides. Alright, right. You see what's happening? I'm considering one interval. I have noticed that equality of the next terms of our function can happen only if the midpoints of these intervals, the values at these midpoints are the same as the value right to it. And I am repeating this procedure for each subinterval and so on and so on. Dyadic fractions. These green points are called dyadic fractions. Since our function is constant on this green set, it's dense in the limit. Since our function is continuous, there is at most one way to extend it from the set of dyadic fractions. So this way is of course to make it constant on the whole interval. And now this procedure works for every k. So let's write it. This works for every k from 1 to up to 2 to the power of n. So we get our result. So f is constant on the whole interval 0, 1, which closes our proof. It was not extremely rigorous, you may say. I agree with it, but I don't want to get bogged down with induction. You can do it yourself, it's not very hard. And that is it. Very nice problem. So thank you very much for watching. I hope that you've learned something new this time, and I will see you next time. Goodbye.